Huh. Draft physics video. Yay. You wonder why. I wonder. Just give up, Gary. They're just never going to get it. You're wasting your time. They're just too stupid. Okay. Yeah, maybe not. We'll see. Yeah, I just can't, it's just so obvious to me. And the more I learn, the more physics lectures I watch, the clearer and clearer it gets, this is the right answer. You know, it's just physics, piece the whole thing together, little crappy bits at a time. And it never did a full review and said, well, let's see what we've pieced together. Let's see what our Frankenstein looks like. And, maybe it needs to be, maybe there's something, we can do to fix it. So, but they didn't do any of that. And then they ended up with this explanation by Einstein of that wasn't even, it's just so obviously not correct. The bent space metaphor relies on gravity to make it work. It's visually interesting. It duplicates, in 2 dimensions what happens, but it's not 3-dimensional. And the real truth is that in 3 dimensions you have to create something that's converging from all directions into something. It's pulling stuff into it, consuming it like a drain. And what sense does that make? A drain to where? How does it just keep pulling on the strings? That's how you end up with the string theory. That's how you end up with all. It's a mistake. And then quantum mechanics became obsessed with this stupid wave crap and just ignored the mechanisms that create the waves, the pressure. And what creates the pressure? Forces. And what do those forces act on? Matter. The wave is incidental. The wave is a byproduct. It isn't the function. And then they went so far as to give this wave property to the smallest things in the universe. Gave them some sort of magical ability to go through space like snakes or something in two different ways at the same time, and all kinds of crap. And just on its face, it's messy looking. So yes, there's a certain intuition. You say, we see the big universe, big clunky things doing really boring things, catch on fire, explode, condense some dust. They don't do anything special. Why is the small universe full of all this special stuff, all these magic properties? Nothing in the big universe is doing this with this component and all of this crap. So yeah, intuition says it can't be right. Yeah, we're in the part of the universe that can get messy because of chemistry. But the cosmological physics and the fundamental physics can't do that. Their properties are simple. So anyway, it's just I don't have a set agenda, but I just sort of have a vague one for this video. I'm just frustrated, and so many things come to mind. I'll just mention one LIGO thing. I have watched a little bit of the press conference, and I took some notes. I don't know if I'll ever get to it though. But there's one point where the guy's explaining his bullshit. And he's talking about he's doing that stupid human hair analogy where they can measure the thickness of a human hair from 4 billion light years or something. And they theoretically they could measure a human hair from a zillion light years, because their theory essentially is that space is made out of steel, and that if something moves a human hair's worth of distance 4 billion light years away, the steel will move here at the Earth the same distance. And if it's a two solar masses worth of hair movement. That is, there's tremendous torque, you know. So if I move the whole Earth a human hair's distance, it's a tremendous amount of mass moving that distance. So the energy would be colossal. And they're doing the same analogy. They're saying this little human hair moved over here, and it moved all the mass inside the Earth enough that they can tell, you know, that their mirror moved a human hair. But that's really all they're saying. They're saying we can see when the Earth, when hunks of rock move the thickness of a human hair. Well, that's not so miraculous, right? I mean, not that we can do it with our human eyes, but it's not. We could certainly feel it if, you know, certain parts of our body might be that sensitive. You know, you get a hair across your ass or something, you'll feel it. But it's this torque argument. A huge amount of mass moving a little human hair's worth of distance is a big event, not a little event. And so this whole contrivance of converting matter into this gravity thing was entirely created because that's not how space works. Space has the inverse square law, and there's no piece of steel moving things. And so all you get is a tiny, tiny representation of that human hair. You get no torque. And so the only way they could create enough torque to move the Earth by gravity, you know, hundreds of millions of light years away, the sun's gravity at the place the Earth is at is 0.01 meter per second or something like that. Very, very, very small. A 30th of what the surface gravity on Earth is. It's just tiny gravity. You wouldn't even notice it if you were floating around in it. You wouldn't know up from down. It's such a subtle amount of gravity. And that's just from the sun. And from the small distance we are from the sun. We're talking about hundreds. That's 8 minutes. That's 8 minutes away. 15 minutes, right? The sun, 15. I don't know, it's a round trip, 15. Well, it doesn't really matter. It's 8 minutes, let's say. 8 minutes. They're talking about 120 light years. Compared to 8 minutes. So, I mean, this event, the only way they can make it move the Earth is they had to contrive a way that much energy can still get here. And I still don't think the calculation can be rational. You know, but it is an awful lot of energy, right? We're going to release solar masses. So I haven't heard yet what the mass is that were, the amount of solar mass destroyed in this collision. Well, anyway, I don't want to get on, I just don't want to, I'm just saying there's so many elements to this are just being glossed over, just slide right over them. Let them say that, let them say that, let them say that, let them say that. These are all just assumptions that we're all supposed to accept, and nobody does any scrutiny on all those assumptions. When they went to go find the event, right? You know, they had a 100 moons worth of sky they were looking at, which is a big, think of 100 moons, it's a big blob out there. You know, it's like a basketball from a couple of feet away worth of sky. What are the odds? If I get all the telescopes on Earth to go look at a basketball worth of space in the sky, you don't think they can find a supernova? What are the odds? 50-50? You'll find something if everybody looks there? We don't know what those odds are. That's what I'm saying. It's like, oh yes, it must be the same event. Just must be because we say so. Yeah. It's really sloppy science. So anyway, so in thinking about my counter theory, I mean, it's just kind of obvious that there's, you know, it's a push universe, not a pull universe. The idea of a converging force going in a drain, going in some place where it never returns, or somehow returns in the back end of the universe, or some kind of wacky thing. Yeah, it's push. Things bang into other things. they push them. There's no pull in the simple universe, in the mechanics of its rudimentary function. And thinking about that further, it brings up the word pressure. So you have the idea that you have to have mechanisms that generate pressure, and obviously my theory creates this kind of two different kinds of reflection. Reflection straight back, and it just keeps going back and forth. And the faster something bounces between something, the closer you bring the two things, the more bounces, and that means more impacts, and that means more energy. So proximity, bringing things close, in a sense, creates energy. Just happens to work that way, a kind of energy. Yeah, and then you have the other reaction, which is a reflection that comes out perpendicular. Instead of something bouncing off, it's absorbed, and instead of releasing it back this way, it releases it sideways. That way, or that way, or that way. And that invents the right turn. And 4 right turns, circle, trap. Energy's trapped. Makes sense. That's what batteries are doing. They're taking in energy. We think it's electrons, but it's really the stuff between the electrons. And it's storing them in circles. It's storing the energy in little circles. Traps. And then when you want it back, you just pull it out of those traps. Just makes sense. So anyway, yeah, I mean, I was never comfortable with their model. I concede. And my discomfort was fundamentally intuitional, and it started with this photon crap. I remember it, being taught this and being just, no. And then I saw the cloud chamber thing with the little particles flying off, and I said, yeah, that's how it works. There isn't anything going like this. There's stuff shooting off of stuff, and it'll move funny, sure, because of charge, but nothing's doing this shit. Anyway, and with time you hear more and more of these wacky theories, the spooky action, as Einstein's brain also rejected, the just gets more and more convoluted, and then the last straw sort of was when I realized they had all these bizarre interpretations of because of the 2-slit experiment. They were inventing many worlds and the photon radar, and then I heard about Huygens, and I'm like, what? You're basing a physics on this completely made up infinite number of mini radar wavies that come off of things. These aren't rational explanations in a sense. I mean, they're so cartoonish, so sci-fi movie or something, so Star Trekky, as explanations that nobody's brain pauses and says, they gotta do a little better than that. That just doesn't, that can't be. And so I was motivated to spend some time thinking and repackaging what we know, and saying, what do we know? We know certain things about these little photons. We know certain things about how energy transfers between magnets. And the fact is, it's much like the Earth. There's no evidence that the Earth burns any energy to have gravity. There's no evidence the sun burns any energy to have gravity. I mean, it burns, but it's not creating gravity by burning. It's creating light. There's no evidence that those forces are coming from inside the things. There's all kinds of evidence that those forces have to be coming from somewhere else. They're being caused by something else. And, you start putting it together and you say, well, there's too much in common. gravity moves the speed of light, magnetism moves the speed of light, and light moves the speed of light. Well, maybe all of them are the same thing. And you start playing with it, and you can make it work. And you make it work well. So, the key thing I've realized is, because everybody's such a child, you can't say something like, okay, let's just call them quantons. Let's call them something, ton. And then they just make fun of it and just play games with it. And you're saying, they just can't, they can't have a mature conversation. And it's a nice explicit word, the idea of a quanta of something. The idea of a true atom again, going back to this idea that let's get to the most basic thing. And the most basic thing is one of these tiny bits, and they call them virtual photons when they're inside of an atom. They call them virtual photons when they're magnetism. These little bits that move the speed of light in a straight line, and they don't hit anything except electrons, or protons. So that's force. So this is one of the things that always got messed up right from the beginning, is that it's not the speed of light. See, we're stuck with the speed of light. But what can be deduced now is it's really the speed of force, because the other forces are moving at the same speed. So why would you call it the speed of light? It's the speed of everything that falls into the category of a force. All the known forces move at the speed of light. And it's a clear distinction between them and the matter bits, which aren't allowed to go the speed of light. By an Einstein contrived rule, I'd argue, where he claims they get too massive. Well, that's really not what happens. What happens is they get too hard to push. So they assume that's because it's heavy, right? So because they can't push it, they're saying, well, it must be because it's so heavy. But it's not because it's so heavy. It's because, in a sense, it's gotten too light. It has so much transparency, it's lost all the bits you need to hit. Most of the bits, when something's moving really fast, it means all the little bits inside of it, most of them are moving the speed of light. So you can't hit them with something going the speed of light, because they're already going the speed of light, technically. And there's so few that are going the wrong way now. So few that are going the opposite way, or this way, or some other way, in the school of fish, let's say. So if you were trying to speed up a school of fish, and 98% of the fish were going this way, and only a few of them had to be hit by other fish and forced to go the right way for a little bit until they go crooked again, they had to be pushed along, let's say. So there's only a few slowing things down. Well, it's really hard to hit them then, because there's so few of them. So you have to throw a hell of a lot more force if you want to try to reform those last few little fish. And so it's not because something got heavy that you can't move it. It's that it's gotten too fast. It's already, that last bit of acceleration's hard to get, because it's hard to hit those last little bits of stuff that isn't moving right. You have to throw more stuff at it to hit something that small. Alright, so what I was thinking was, first, it needs to be called the speed of force. At least I'm going to try to keep doing that. And, just lost what I had. It's the speed of force. There's another point to be made about the function of it. Well, hopefully I'll remember it, get back to it out of place, but it'll have to be out of place. That's a good point. I really like to finish it. Okay, yeah, so it's force. So let's call it the speed of force, and let's understand the difference. There's only two things in the universe. There's force bits, quanta, quantons, and they fall into the category of all the virtual stuff plus photons. So all the visible light, all the whole electromagnetic spectrum is force. Light should have never been called something else. Shouldn't be in a different category. It's a force. And we happen to have an eyeball that can perceive the force. So we can see the force, a force. Can't see magnetism, can't see gravity, but it can see light. And so all you have is the force bits, and you have matter bits, the electrons and the protons primarily. And you don't need to worry about the stuff inside. It's okay if there is stuff inside, but it's, you know, you can have it or you don't have to have it. I don't think that it's necessary to try to blow electrons and protons apart and talk about quarks and all that stuff, because I don't think they're things that exist when the thing isn't shaped. They don't have any lifespan. They're just force, essentially. I think once you break them out of their native habitat, which is being an electron or being a proton, having them combined. But there certainly would be three of them in principle for quarks. The idea of the three dimensions. Quarks that go this way, quarks that go this way, and quarks that go this way would be the idea. But anyway, so all you have is force bits and the matter bits. And that's it. There's nothing else. You can talk about atoms and stuff like that, because that's swell. There's certain arrangements that they're going to get into because they're just conducive to the geometry. And I would argue that a neutron is like that. A neutron is just an electron and a proton that are in an arrangement that's solid, that's hard to break once you create it. Now they'll decay out of the environment of an atom, but I just mean when they're in an atom, their space is controlled and their structure is solid. Let's put it that way. Alright, so all you have is force bits and matter bits, and all you have to do is account for the movement of the force bits between the matter bits. The force bits are what gives the matter its identity, its velocity. Everything a matter bit does, it does because a force acts on it. And the force bits can't act on each other, as I've pointed out, and I'll repeat. So the matter is just a conduit between force, interacting with force. So when a piece of matter does something over here, it changes force, and the force communicates to another piece of matter that something over there happened. And there's rules to that, the inverse square law, all kinds of other rules about how those communications take place. But between electrons, there's no inverse square law. The inverse square law only comes up when you start scattering force. Alright, so yeah, I'll just do the force and matter thing. So matter, the force bits only have two identities. Right? So I could draw it, I'll just draw 4 of each, and you'll have to just imagine the whole universe full of this stuff. No need to get crazy, right? So the force bits come in two types. Two polarizations, it just doesn't matter. Two orientations. It could be round and square, you know, X and O's. It can be arrows, it can be color, it can be geometry. This way versus this way, flying. Something like that. They're polarized. And then we do one thing. They move the speed of light in a straight line. And they'll keep doing that forever until they hit an electron or a proton. If they don't hit an electron or a proton, they just keep going in a straight line forever. And they're the only things that have perpetual motion. They're the only things that just do this one thing. They move the speed of light. They move the speed of force. And that's it. They don't do anything else. They don't have any other property besides being polarized, one variety or the other variety, and they move the speed of light. That's it. That's all the forces. Light is just those things at a frequency. The black ones. Just FYI. So anyway, alright, so you have the matter bit. And now we'll describe the interactions that take place to a matter bit. So we have a matter bit, let's say, there's all kinds of force hitting it all the time. So understand from this argument that it means that every place in space, every point, no matter where you would go, there's an equal amount of this force that will hit you. So if there was nothing disturbing the force, everything would just get hit with exactly the same amount of red and black. Nothing would move. Everything would just do that. It would just sit in its place and get hit by the force. Now, if you got close to something else, then we get into this more complex argument that you would shadow each other from force, and therefore the external pressure would push you together. And that's essentially what's happening in gravity, but it's not really pushing, it's an absorption, as I'll explain. Alright, so let's say the electron is the black, we'll say this polarization, the black polarization, and the proton will be the red polarization. So we'll just do the electron example. The proton does exactly the same behavior as the electron, it's just the colors are reversed. So let's say an extra black bit has been sent the way of this electron. What's going to happen to the electron? What does the electron do? What's the reaction? Well, the reaction is something comes in, something's going to have to go out. And the go out is a reflection. Now, the consequence of that reflection is that if there's another electron over here that sent this arrow, it means these two arrows are just going to keep going back and forth and back and forth and back and forth. And that's the creation of pressure. And as I stated, as you bring them closer and closer, these arrows will bounce more faster and faster, and there'll be higher pressure. And that's also creating the frequency of what you call a photon. So a little ray of infrared light really represents a distance between two electrons. And when one of the electrons moves, it will release at a frequency this stuff caught between it. The pressure. Alright, and the pressure is the resonant frequency it obtains is based on the fact that these electrons are not really rigid in their shape. They can have any shape, and depending on how they've been formated, they will absorb, the arrow will reflect deeper inside of them or further out. So if an electron hits here, it reflects sooner. If it hits deeper, it reflects later. And through that mechanism, these reflections end up being all in phase eventually, especially as something goes from wide to narrow. The phase of the rebounds will end up becoming consistent because of the motion of the electron, its vibration. So, but that's a whole nother, it's a little complicated, so I don't want to get into that, but that's how that gets on that's how the phase becomes consistent. So anyway, the argument is, okay, so the electron gets hit, and what's going to happen is it's just going to release the same electron, the force bit hits, the electron just reflects it, so there's your equal and opposite reaction essentially. But what really happens is that the electron is going to, we'll just redraw it down here, the electron is going to absorb the energy going this way, and now this will be part of its identity. So you have to kind of think of the electron inside of it as it has these little arrows moving in all directions inside of it. And so it essentially has motion in all directions going out. And you can sort of imagine if I give it extra length this way, then it'll tend to move this way. And if I give it extra length this way, it'll tend to move this way. And so you can get the idea that this is like a gyroscope of sorts, and that it does the addition of what the momentum of the electron at any particular time is going to be. And these are just kind of, you could say these are the quarks. They're just stuck. These are force bits that are just stuck to each other in a direction. And what's going to happen when the force bit comes into an electron, it's going to add a little bit of force onto one of those quarks, onto one of those internal elements, and it's going to release one going this way. So it's going to give back one it had going the opposite way and keep this one going forward, which will give it a little bit of momentum forward. So there's an extra bit of kind of energy, but it's not really energy because all you're doing is exchanging. So although you're saying, well, look, that's three arrows. You know, one goes in, one comes out, and you've got an arrow going out this way. Well, it doesn't really go out. It stays inside. It's an exchange. It gave this one to the universe, and it took this one from the universe. And that's what really happens. So there is no imbalance. There's no conservation violation. It's one for one. Now, the momentum of this electron won't be permanent because, as I pointed out, there's always forces hitting from all directions, and these ones coming from the sides will degrade that velocity, and I'll explain that now in this second. So this is one reaction electrons can have, and here's the other reaction they can have. So we're still using black. So an electron gets hit with a red arrow, a piece of red force, polarized red. Now, when the electron gets hit by red, a different kind of absorption happens. So now, instead of creating a reflection, that red arrow will come out perpendicularly. So it could be this way, could be this way, out of the paper, into the paper, this way or this way. So in one of the four other quadrants is where that red arrow will go. So instead of reflecting back, it reflects essentially perpendicularly. And the same thing is happening. What's really happening is there's there was a black bit inside of the electron, because it's made of black, that was going this way. And what's really happening is the red bit will come in and exchange. So it's the same process. There's just an exchange. So just like this exchange was for something forward, something back, this one's going to exchange when it's a wrong color, you know, a contrary color. The reflection is just out perpendicularly in the sense that what's going to get exchanged is this black arrow is going to take the direction of the red one and go this way, and the red one's going to take the direction of the black one and leave perpendicularly. So in a sense it's the same conservation. One thing goes in, one thing comes out, and there's a little momentum gained by the electron technically because it exchanged something going some other way for the new direction going this way. Now, what's happening is as stated, there's always field energy coming in from the side. So when an electron or a proton gets any momentum, it usually can't keep it because essentially any imbalance it has. So let's say you have an electron that, and it's going to be probably misshapen by the process. So let's say it has extra arrows going this way. So it has a plus amount of arrows going this way. So it moves this way. Well, when the field energy comes in, the red bits especially, black bits really won't have any effect, but the red bits will see that momentum and fight it. So this happens with magnetism, and the current, the magnetic field that's created that ends up fighting the movement of the electrons. And this is essentially how the movement of the electrons is fought, is the red bits are coming in from the side, and just by laws of probability, because there's more black bits going this way than black bits going this way, by the laws of averages, it will hit these more often, the ones going forward, and create energy that goes out perpendicularly, but let's not confuse things. Anyway, it's going to cause an exchange with these arrows more often than with these arrows by the laws of probability until it neutralizes it back to even. So there's a tendency for the electron to be forced to be neutral in its movement. So for it to continue moving, it needs to constantly be hit by force. Force has to keep coming at it to keep pushing it. And as soon as the force stops, the electron will stop. I mean, it won't stop immediately. It'll stop as soon as it gets enough red force hitting it to make it stop. And the only way it can keep moving is if there is no red force hitting it and there's just black forces hitting it. But that's a hard environment to create. And so the same process happens with the protons. And as I pointed out, the relationship between the electron and the proton ends up clearly demonstrating the mechanism of attraction, in the sense that there can't be any blacks reflecting here. So anything black that goes into the red comes out some perpendicular way, and any red, okay, there can't be any reflections, so nothing goes back and forth. Anything red going into the black ends up leaking out perpendicularly. So you can never have anything bouncing back and forth. No frequencies can ever be created between them, so there's no pressure. Very little pressure can be maintained between an electron and proton. So the external forces that are always present and strong will be affecting both of these objects, and so you have lots of pressure on the outside, no pressure on the inside between them, and they will acquire more and more arrows and move. They will gain velocity through acceleration and move towards each other. And that's the force that holds atoms together. And the repulsive force, as I pointed out, is just the simple logic of, you have two electrons and there's just a constant reflection back and forth that keeps them from getting any closer. And the way you can disrupt that is if a proton slides in between two electrons, or you end up with two electrons on either side of a proton, then these electrons can get into a much tighter orbit, because now there will be leakage. The black force will leak out through the proton, and they'll be able to get much closer. And in that circumstance, they might need a velocity to stop them from getting too close. But I think there's always residual. So there's always just some random field. The field is still producing red arrows on this electron. And so the trick would be is that the red arrows will bend and hit the proton and then reflect back and then go out the electron again. So you do have some pressure that will stop them from crashing into each other. So this explains, when you can logically see how this creates the forces of attraction and repulsion. This mechanism is what magnets capitalize on. So the field energy comes into a magnet, and what's really going to end up happening is, depending on which part of the magnet the thing leaves last, the magnet's going to end up converting all the force that comes out of the one side, the black side, into black, and all this stuff that comes out of the red side into red. So it's coming in random here. That's, and this is happening to both sides, obviously. So you have a bunch of random stuff coming in here, mixed, and it comes out segregated. And that means if you have another magnet of the same of the same arrangement, oops, gotta do it red, Gary. So if you have another magnet oriented the same way, you can see that the reds are going to be shooting red at each other, creating a ton of reflections. The blacks are going to be shooting blacks at each other, creating a ton of reflections. And it's going to create a tremendous amount of repulsive force. And obviously if you turn them the opposite way, you have exactly this situation again where everything leaks out. The black energy leaks out of the red energy will leak out of the black, and you have attraction. So this model, it fits all the physics in a general sense, all the general principles, all the Maxwell phenomenon, explains all the Gaussian how the force, when the more you spread it out, again that's just the inverse square law, but you can just see how it's just a force. It's just radiating like a light bulb. That's why a light bulb does the inverse square law. It's because the magnet's actually radiating this segregated force. If we could see it, if our eyes could detect, say, just black or just red, we'd be able to see that it's getting segregated. We just can't see it, but it's right there in front of us. So I mean, you can hold a magnet, and if we had a different kind of eye, we could see it radiating, these different colors. And it's not doing it because it's creating energy, because it's burning some matter. It's doing it because the stuff is always coming into it randomly. I mean, that's probably why we can't see gravity, is because we'd be blind, because it's so thick. The universe is so thick with it that you couldn't ever, it's like technically an image of me is being cast onto this screen. So there's light reflects off of me, it bounces back onto that screen, and there's an image of me in there. But you can't see it through all this noise. All of that is much louder than my image. And the same thing would happen is that if we could actually see, polarization, we could see the difference between a black and a red, and we could see it in the field of, the density of the field is so strong that even if I had a strong magnet in front of me, it would be weak compared to the amount of light that's being cast by the universe. So that's probably why we don't have it, is because it wouldn't work. It wouldn't be functional. You could only see very, very close up. It wouldn't be a good eye. But it's there. It's all, that's what's holding us together. It's what moves everything to each other, and it's what shoots things away. It moves, when my hand moves, there's a bunch of these little bits that are shooting through channels of protons and electrons, and they're causing atoms to expand, and they're causing all kinds of things to happen, and all that force is a real thing. It's like light shooting through me. I'm made of it. Everything's moving the speed of this force internally, but it's just trapped in these, again, the key thing is this right turn. This right turn that the red force takes, or the black force in a proton. This right turn. This is our economy. This is the universe having a capacity to create, again, the circle. The trapped bit of force. The four turns. And that's a little bit annoying. It's a battery. Yeah, okay, stop. It's an old battery booster thing, and it's, you know, the battery's been dead for a year, but it just does that now and then with this beeping shit. Yeah, you know, it's just annoying. Anyway, so that's probably, I don't want to, I mean, it's exhausting going through all this and trying to order it and make sense of it, but I'm just saying, this is so obviously a brilliant answer. It answers all the questions with a little rational, simple process. You know, simple properties for the force bits. They move the speed of light. They contain just one quanta of energy. They can move at a frequency and create what we call photons. And then you have they're polarized. And then you have just these two matter bits, the electron and the proton. And depending on how you arrange them, they can make high pressure or low pressure. They can be close together or be forced to stay far apart. And that's your atom. And the force is inside of that. The force travels the right turns. Yeah, it's just explains magnetism, explains gravity. I mean, gravity's in here, so gravity's got a catch that there's no polarization of the electrons and the protons. They're unlike a magnet. They're not arranged. You know, a magnet arranges protons and electrons in an order. You know, plus minus, and regular matter doesn't do that. So regular matter can't take full advantage of the fact of this leakage process, you know, where the force leaks. So in regular gravity, I guess I can do it real quickly. The battery's going dead. You know, so with two gravitational bodies, what ends up happening is some of the black force, okay, so if let's say this is black energy going across, it could hit an electron or it could hit a proton. Now, if it's an electron, it bounces back. And then this one, it could hit a proton here, and that means, oops, it's going that way. So you see that it can't build up any pressure. So, you know, it leaks half the pressure. So that's why it's so much a weaker force. Is because there's still some pressure, because just the law of averages are 50-50, you hit an electron versus hitting a proton. But so you can maintain a little bit of pressure, but it's not much, and it's certainly not enough to overcome all the external pressure. And so what happens is you end up absorbing this velocity, and when you absorb arrows, that means this side doesn't get hit by them, and that means it absorbs arrows in response. So it's just by the law of averages. When there's more pressure on one side than there is the other side, you'll absorb arrows where there's more from the side that's more pressure. So you'll end up having a velocity. All the little bits, of course, this is just what happens to electrons and protons. The electrons and protons will gain the velocity because there's going to be more pressure out here than there will be in here. But it's not a strong lack of pressure because there's no direct red on red or black on black. Alright, that's good enough. So it explains it. Explains gravity. Explains magnetism. Gives you a rock solid mechanical explanation. No more bent to this. No more expanding space and mushy bush. It's solid. And this obstinate pretense that somehow this doesn't make sense, this doesn't fit, this isn't a great model if it's true. I mean, not to hear any kind of, you know, for people to be so outrageously mocking and dismissive when it answers the functions, when it provides an answer. Why it happens. It explains why it happens. It does what Newton couldn't do. It explains how the gravity works. How the magnet works. And to be mocked for this? Yeah, I should be indignant. What kind of creatures are you? It's just disgusting. You know, these questions have been sitting out there for thousands of years. I gave you a really rock solid material answer, and you're running from it like you know, the Pope runs from evolution. It's just disgusting. Yeah. So anyway, yeah, that's enough. But I shouldn't have to do this for fucking 7 years arguing this shit, or whatever the hell it is, 6, 5, whatever. You know. Enough said. So, until next time, such.